and moving into the environmental section. And from the first presentation, I think we had given an overview of the challenge that we would have. So I'm going to say that on the Concawe side, we have addressed this challenge by using the hydrocarbon block method for PBT assessment of petroleum substances. So let me just remind you what the challenge was. It was how to progress PBT assessment of petroleum UVCBs in a scientifically sound, regulatory acceptable, and timely manner, taking into account the fact that we cannot identify all constituents analytically. So just to give a little bit of background, according to R11 guidance, the recommended approach, one of them, is to assess PBT properties of complex UVCBs through fraction or block profiling approach. And so the substances that can be divided into fractions or blocks in which constituents are structurally similar, so this is recalling the discussion that we had earlier, or in which the constituents are to such an extent similar that their degradation, bioaccumulation, and toxicity properties can be predicted to follow a regular, predictable pattern. So for Concawe, we've adopted this approach in the form of the hydrocarbon block method. In this method, we use an analysis by GCGC to separate out petroleum substance constituents based on volatility and polarity. And this is what Carol had discussed in the first presentation. So this analytical information translates into carbon number and chemical class. However, we understand that volatility and polarity, these physicochemical properties, are not always sufficient to ensure structural similarity. So for PBT purposes, with near-eluting constituents on the GCGC, we don't have the detailed analytics that will give us constituent-level information. And additionally, something that we will hopefully discuss at length is that we do not have a pragmatic definition for similarity of constituents within a block. So this is really reflective of the conversation that we had earlier on similarity. So the specific challenge questions that we have are considering the complexity of petroleum UVCBs, how can we bridge the analytical capabilities that we have and the requirements of the blocking approach for PBT assessment. So that's persistence, bioaccumulation, and toxicity. So always in this presentation, we will be talking through a PBT lens. So specifically, what would be the criteria for homogeneity of a block? So just recalling from the previous slide where constituents are structurally similar, etc. And once we've decided that this is what a block is going to be, how do we choose what would be a good representative constituent of that block? So I want to step back a little bit and give some more information about Concawe's hydrocarbon block method. As mentioned earlier, our petroleum substance contains hundreds to millions of constituents, right? So we've got some options on how to address UVCBs, as mentioned. There's whole substance testing, and this is a bit the approach taken by human health that was discussed earlier. We also, on the environmental side, are developing a more tailored approach for persistence and bioaccumulation testing with constituent tracking. This is ongoing work. It's not finished, but I wanted to mention it in case anybody wants to ask me about it offline. We also have the option of focusing on known constituents. Unfortunately for us, petroleum substances are just too complex. There's not one constituent that comprises a majority. We can also then use a block profiling approach, which, as I mentioned, we do so with the hydrocarbon block method. This works well for us because petroleum substances are basically different types of hydrocarbons. So we can use an analytical method to divide these constituents into blocks. In these blocks, because the constituents are grouped, it simplifies the number of entities that we have to assess. And every constituent in a block, therefore if a block is homogeneous, is supposed to be representative of that whole block. This allows us to capture variability in substance composition, because if we are grouping like constituents into a block, then variation in those constituents will be dampened by the fact that those constituents are grouped in a block. And so the diagram on the right just gives you an idea of the complexity of substance that we're dealing with, lots of constituents, and the way that we're able to separate them via GCGC. So I'm going to give a little bit more detail on how we do our block separation. So as mentioned before, polarity and volatility are the two axes that allow us to separate our constituents by chemical class and carbon number. We're assuming, so let me just drop down to the diagram here. So we can then take, if this is this whole thing would be one petroleum substance, we can then divide it up into blocks. The percentage of each block can then be allocated into a chart. So in this case, we are concentrating on, for PBT assessment, carbon numbers C6 to 30, and these chemical classes. This is not everything. Obviously, we've made choices here. It's not things that are lower than C6. It's not constituents that are higher than C30. And that's because we had decided that these were the most relevant for PBT assessment. So most petroleum substances are then resolved into these selected hydrocarbon blocks with GC-GC analysis. And we assume that the constituents in the block, of course, will have similar fate, hazard, and risk. We then, for each block, assess either via experimental data or QSAR the properties of that block for environmental hazard and risk assessment. So just to give you an idea of what is in a block, let's take the C26 naphthenic diaromatics as an example. I have on the right-hand side of the slide a number of different structures that would fall into this block. So you can see that there are different levels of alkylation. The cyclics, you could have C6, you could have C5, but they would all be grouped together in the same block. For this particular block, there is about an order of magnitude or more range in the predicted biodegradation half-life. So there's a big range there, but the conclusion for the block is that all the structures that would fall into it are considered PVP, and this is based on QSAR and experimental data for all of the naphthenic diaromatics greater than C15. Similarly, on the bioaccumulation side, we do have a smaller range of predicted bioaccumulation, but again, based on either QSAR or experimental data, these structures in this block are concluded not be. So at some point, we have to ask ourselves, at what point is it okay to have some variability in the predicted outcomes if it's going to end up with the same kind of assessment? So I wanted to show you then what is in the 2019 Concawe PBT report. So this is where we're using the hydrocarbon block model. We have the carbon range and the classes that I'd mentioned earlier, but to populate them, we generated 16,000 hypothetical constituents. So these are hypothetical in the sense that they were generated using computational and statistical models. It's only 16,000, all right? So we just said that there are hundreds to millions of constituents. However, with these 16,000, we recognize that this is a small subset of possible petroleum substance constituents, but this still allows us to make some conclusions on the blocks. So we then take these 16,000 constituents, some of which have been confirmed to be in petroleum substances, and some of which we are not able to analytically confirm. And so then we have allocated them to their respective blocks, and then assessed for each block the persistence of the constituents that we've now stuck into that block. We assess their persistence based either on experimental test data or on QSAR. For persistence, we have a lot of experimental data. And so the majority of the information that we have is from testing, unless where you see a little red asterisk, and that is when we have generated the data from QSARs. So the blocks in blue on this chart are those that are assessed as persistent or very persistent. You will note that most of these are based on QSAR data. And that is because it is difficult to test these constituents. They are harder to obtain and they are difficult to physically test. We then do a similar analysis for bioaccumulation. So if blue indicates persistence here, green indicates bioaccumulative or very bioaccumulative. And then the blocks in pink are those where they are both bioaccumulative and persistent. So those blocks that screen persistent and bioaccumulative are the C14 to 19 polynaphthenics, the C19 monoaromatics, and the C17 to 18 naphthenic monoaromatics. So then these blocks were the focus of a toxicity assessment. So based on test data again, and on the target lipid model, these blocks were assessed and none of them came out as T. So we have no blocks in the 2019 PBT report that screened as PBT or VPVB. And obviously this is subject to change with new data. So now to go to some of the questions that we'd like to raise in the hydrocarbon block method. So we had talked earlier about structural similarity and how this can define block, well, for us, we would like to see how this could be defined for block homogeneity. As mentioned earlier, in our current approach, the substances are divided into blocks based on GC-GC. Therefore, we know that the constituents in a block share polarity and volatility, but not explicitly structural similarity. So there will be cases where things that are not structurally visually similar would be put in the same group. For example, the naphthalenes and the biphenyls. We also would have structures with different alkylations put in the same block. For example, if you have a structure with 5 methyl groups, it would be in the same block as the same backbone structure, but with a pentyl group. However, every constituent in a block is supposed to be representative of that block. So with that in mind, and with the idea that we're using this for PBT assessment, what variation in properties is acceptable in a block? We don't really have a practical definition for similarity for our substances. So then the question is, all right, let's get a little bit more specific, a little bit more into the details. What metrics could we use for similarity? Should we be using phys-chem properties, which is kind of the approach we have now with polarity and volatility? Could we be looking at biological, ecotoxicological impact? So previous proposals have suggested that constituents within a block stay within a certain range of biodegradation half-life or certain range of KOW. Should they be structurally similar? And so this really is getting into the details that we were discussing earlier of, well, what does that mean exactly? Does it mean that they have to have a similar functional group, a similar maximum diameter for the molecule, a certain type of steric hindrance, etc.? And so I'm hoping that in the conversations we can really get an idea from you, the audience members, of which of these would make the most sense, or should it be a combination? And then once we've decided on the metrics, what range of variation is acceptable? And can we support the metrics that we decide upon analytically? There's a second set of questions that we would have also, which was, once we decide on the blocks, how do we choose representative constituents? So right now, in this graph on the right, we've just placed the hypothetical library into more or less the blocks that they would belong in. So we have many representative constituents per block. But how could we confirm that the constituents that we have here are really in a petroleum substance? Can we do some work on a whole substance to inform our choice of representative constituents? If we have a homogeneous block, is one representative constituent okay, good enough to represent the whole block? And maybe we can push the comfort level with this. If one of the higher carbon number blocks, as was explained earlier, we would have more expected constituents. So would we be comfortable with one constituent for a block that is homogeneous, one constituent representing thousands? And then if the block is not homogeneous, what would make a good representative constituent? Something that's the most prevalent or relevant, occurs in the most petroleum substance, or the most conservative? And then how can we bridge the analytical capabilities that we have with the requirements of this new blocking approach? And so that is the end of my presentation. And please do start to put your questions into the chat or your ideas. And we can come back to those after we have a presentation from Vincent Bonhomé from ECHA. And so Vincent, I give you the floor.
Thank you, Delina. Can you hear me? Okay, yeah. So I will provide a short refresher on very basic stuff on the PBT assessment of UVCB substances. So the topic today is really focused on the PBT assessment, but it doesn't mean that there is no other information requirement, in particular those from Annex 7 to 10. But that's another topic, and I will not talk about this today. So next slide, please. So the background is, of course, Annex 13 of REACH. And according to the legal text, PBT assessment are actually a chemical safety report on the chemical safety assessment are required for tonnage above 10 tons per year. And this chemical safety assessment, chemical safety report requires that the PBT or VPVB assessment is performed. So this means that as long as you have Annex 8 dossier, so with tonnage above 10 tons per year, you can be requested to have higher tier information, even if it's not in the standard information requirement, if it is needed to clarify the PBT concern of your substance. Again, maybe this is something that is very well known, but this is just a refresher just in case. Another thing that Annex 13 is saying is that a tiered assessment is possible. Annex 13 makes a clear distinction between screening information and assessment information. And I will develop a bit more later on this. The two other points I would like also to discuss today is what is the scope of the PBT assessment. On Annex 13 is pretty clear on that. It's every relevant constituent of a substance or every relevant transformation degradation product. Again, we will discuss this extensively later. And the last point, which I wanted also to remind, is that the data obtained should be obtained under relevant conditions. And relevant condition is not necessarily representative conditions. I mean, it's relevant for the purpose of the PBT assessment. Next slide, please. So first, I will talk a bit about screening information, what is meant by screening information. And you can find more information, more details in our guidance document R11. So screening information is obviously screening studies. It could be QSAR, it could be other kind of adaptation, for example, in vitro tests. But to keep it simple, just to focus on the most usual ones, for the persistence assessment, it's in most cases it's screening biodegradability test, either ready, inherent, or enhanced biodegradability test, if they are applicable. And this is a big if for UVCBs because it's really the case that they can directly be used for UVCBs. Example of screening information for bioaccumulation is based on log KW or log KOS. Sorry, there is mistake in the slide. So if you have a log KW above 4.5, it means that the substance screens for B. Or if you have a log KOW above 2 and a log KOA, sorry, it's KOA above 5, than the substance screen for bioaccumulation in air-breathing organisms. Just the point that I just focused there on the persistence assessment and the bioaccumulation assessment, and toxicity is actually not so necessary at the screening stage, because if you cannot say whether the substance is P or VP or B or VB, I mean, the substance could be VP, VB, and you don't necessarily need to investigate the toxicity at this screening stage. But it doesn't mean that if you have information on toxicity, of course, this is something to be reported, obviously. Of course, screening information, as the rest of information, must be properly documented. It should be relevant, I mean, for the purpose of the information requirements. I mean, if we are asking, I mean, if the legal text is asking for biodegradation, you are not supposed to provide dissipation. The information should, of course, be reliable. So, for example, if you are using QSAR, you have to take care that it is in the substance is in the applicability domain of the model. You have also to quantify the uncertainties of your prediction. And maybe I can develop already a bit about that. You can have, of course, screening information that are in one way under conservative or in other way over conservative. If you have an approach that you know is consistently under conservative, but you have a result which is positive, you are pretty confident that, okay, even though my method is under conservative, I have a positive result, then my substance definitely screens for PBT. On the other way around, if you know that you have an approach which is consistently over conservative, and you get a result which is negative, then you are pretty confident to conclude that, okay, my substance is probably not PBT. So this is the whole purpose of screening information. And of course, what we want to avoid is to have, well, of course, false negative. We don't want to be in a situation when you conclude that the substance is not PBT based on screening interaction, where actually it is PBT. And the other way around, if you have false positive, in practice, it can create difficulties for SVHT identification, because you just cannot identify a substance as a substance of very high concern if it's just based on screening information. So, I mean, false positive are not necessarily, it's also something to avoid. And yeah, the last point is, okay, Annex 13 allows you to use screening information, but if you have in parallel assessment information, meaning IRT studies, this IRT information will always prevail over screening information. And I can even say that this has been recently confirmed by a judgment of the Court of Justice on phenanthrene, because this was exactly the situation that there was a simulation test available indicating that the substance could be P, but in parallel there was a screening information indicating that the substance was readily biodegradable. So this was clearly conflicting information. But the court clearly said that assessment information has higher value than screening information. So next slide, please. Assessment information, I will be quick on this because you all know what it is. I mean, these are IRT studies. So typically for a persistence assessment, it's a simulation test in 3 compartments. For bioaccumulation, it's bioaccumulation studies. And for toxicity, it's long-term aquatic toxicity or chronic aquatic toxicity on 3 trophic levels. And as well, human health. It also includes some human health endpoints. Just to be clear that QSAR are not considered assessment information. It's nowhere in the legal text that QSAR are never mentioned as assessment information. And of course, they can be considered in a weight of evidence. But again, I would like to repeat that higher tier studies will have much higher weight compared to other kind of information. Next slide, please. So, yeah, the main points. We have discussed this morning extensively the UVCB nature of the PETCO substances. I would not like to repeat everything that has been discussed this morning, and especially what was already presented by David. I mean, in large part, it also applies to environmental endpoints. I would like to focus instead on what kind of guidance is given in guidance document R11. So basically, they propose different kind of approaches to assess the UVCB for the PBT assessment. So first is the known constituent approach. That is that you assess, you make the PBT and the PDB assessment of each and every constituent of your substance. But I think you are all convinced that this is not really feasible for PETCO substances because there are simply too many constituents in those kind of substances. The other approach presented in guidance R11 is a fraction profiling or block profiling approach. In this approach, the PBT, VPVB assessment is done on the given fraction, and it relies on the hypothesis that the PBT, VPVB properties of this fraction or this block is the same or follow a regular and predictable pattern. Another approach is the whole substance approach. You mean that basically you just test the substance as it is. But for the PBT assessment, in most cases, it is not adequate. I mean, it will be adequate only if you are sure that you have a substance that is homogeneous enough. I mean, homogeneous in terms of PBT, VPVB properties of all these constituents. And as you can imagine, I don't think it is the case for any of the PETCO substances. And of course, it's possible to have a combination of those different approaches. I just want to highlight that either for the constituent or block approach, it's possible to assess each and every constituent or each or every block, but it's also possible to assess, to define the so-called lead constituent or lead block, lead fraction. And if you can establish, if you can establish that it will represent a worst case situation. So if you can demonstrate that your constituent or block is most likely to be PBT VPVB, then you can conclude with confidence. You can test and conclude with confidence with this constituent or with this block. But again, it looks easy in theory, but in order to demonstrate this, it would mean that in practice you have to generate some data. There is also another situation. I mean, it's not necessarily just worst case, but if you test a constituent or block and it's most likely not PBT, you assume that it's most likely not PBT, but the actual experimental result shows that it is PBT, then you can conclude in this situation that the substance you should conclude that in this situation the substance is PBT. Next slide, please. Yeah, so this is my last slide. Actually, I just want to make clear that in any case, of course, the substance must be relevant and must be reliable, of course. And in particular, the information requirement should be met. So as I explained before, for example, for the PE assessment, what is expected is to have information on biodegradation, not dissipation. So it means that whatever testing strategy you choose, in the end, you must ensure that what you have tested is actual biodegradation. So it means that potential volatilization, non-extractable residues, or any other losses should be quantified. And yeah, the last point about the relevant condition for the PBT-VP assessment. I mean, it's probably very well known now that we expect for persistence assessment, for example, to have the test temperature to be 12 degrees. And I mean, this has been validated again by a judgment of the Court of Justice. So yeah, again, this was just a reminder. And yeah, this is my last slide of what I wanted to present. Thank you.
Thank you, Vincent. And maybe now I think we can, in the program, go back to some of the questions that were posed. And if people want to put in their questions in the chat,